So good afternoon, all of you. So we'll continue the class. So morning we have discussed about mechanical properties of fluids, introduction, and fluids classified into liquids and gases. After that we discussed about what is mean by fluid and what is mean by fluid statics and fluid dynamics. And after that we started studying discussion about the density of fluid and relative density. And after that we are discussing about the pressure of the fluid. So at pressure, I think we stopped the time up so that we can continue now. Yes. So the pressure of a fluid. So already pressure we defined pressure P is equal to so force acting normally per unit area of the container F by A. Okay, and its SI units also we have described pascals or Newton per meter square. SI unit is Newton per meter square, that is equal to 1 Newton per 1 meter square is 1 Pascal. So that is represented with PA, 1 Pascal. And CGS unit is that dyne per centimeter square. Okay. And after that, we are trying to relate Newton per meter square and dyne per centimeter square. Suppose 1 Newton per meter square you can take. So 1 Newton is equal to how many dynes? 10 power 5 dynes. Do you agree this? 1 Newton is equal to 10 power 5 dynes? Yes or no?
Yes.
Sir.
Right. 10 power 5 dynes and 1 meter is equal to 10 power 2 centimeter, 100 centimeters whole square. This you can write 10 power 5 dynes divided by 10 power 2 whole square, 10 power 4 centimeter square. So 10 power 5 by 10 power 4, 10 power 5 minus 4, that is 10 power 1. 10 power 1 dyne per centimeter square. Okay, so that 1 Newton per meter square is equal to 10 dyne per centimeter square. This is about the relation between SI unit and CGS unit of pressure. Next you can see the one more unit called atmosphere. One more unit is atmosphere. 1 atmosphere is equal to one more unit of pressure. Fluid pressure is atmosphere. 1 atmosphere is equal to 1.013 into 10 power 5 pascals. 1.013 into 10 power 5 pascals or 1.013 bars. 1.013 bar or 1 bar is equal to 10 power 5 pascals. Okay. So this is about another unit to calculate the pressure of a fluid or pressure of a liquid or pressure of a gas. Or by using mercury level also you can see the pressure value that we can see later, because once variation of pressure with height if you can see, then I can tell you that one. So this is about the units. Then the dimensional formula you can see. Dimensional formula of pressure. So here you can see F by A. F is the force divided by area. So dimensional formula of force, you know the m power 1, directly I am taking L power 1 T minus 2. I remember dimensional formula of force m power 1 L power 1 T minus 2 divided by dimensional formula of area L power 2. So this we can write as m power 1 L1 divided by L2, that is L minus 1. Because L1 minus 2, that is 1 minus 2 minus 1 and T minus 2. So you can see here dimensional formula for pressure is M1 L minus 1 T minus 2. M power 1 L minus 1 T minus 2. Okay. So this is about the dimensional formula of pressure. Okay. Are you clear up to this? Yes,
Yes, sir.
very good. So next we'll go for continuation. So pressure is a scalar quantity. Pressure is scalar quantity. Scalar quantity. It is not a vector. This diagram will tell you why I have given. Next, if we can see some examples to understand the pressure more detail. Some examples. Example 1, if you can observe a sharp blade or a sharp knife. A sharp knife is more effective in cutting anything, like cutting vegetables or cutting any object. More effective than a blunt blade, a blunt knife. This is an example related to pressure. But I said a sharp blade or knife is more effective in cutting than a blunt knife or blade. What is the reason here? Difference between sharp and blunt. So here, if you are taking a knife like this, okay, this has a sharp edge. Okay, so that what happen at the cutting, this is like a knife, and there is a cutting wood or cutting whatever you can trying to do here, like this. So here, where this force acting to cut that per unit area, you can observe here. So that means you are applying pressure here, force per unit area of the area of cross section of the knife. Suppose in this case, you are applying the pressure same for sharp knife and a blunt knife. Then sharp knife easily cut than blunt knife. Why? Because you can see here. Pressure is same, you can imagine. Okay, sorry, force is same. You are applying force is same. Then pressure, how it is varies. So you are pressing force is same to cut the vegetable or to cut any log. So force is same, but the knives are different. You can take sharp knife and a blunt knife. Then sharp knife easily cut, but a blunt knife not possible. Why? Because you can see our area where it is touches the knife, that area of cross section is for sharp knife is area of cross section is less. For sharp knife is area of cross section is less, force is same. So if area of cross section is less, then pressure increases. Pressure increases. Suppose you can take for a blunt knife, same force applied, then area of cross section is comparatively high with respect to sharp. Force is same. In that case, area of cross section is more for a given force, then the pressure will be decreases. And the pressure to cut the log or to cut anything is decreases, so that it is not effective to cut. Are you clear this example? Are you clear this? Understood or not? Right. Similarly, you can take one more example to understand the pressure. Yeah, very good. So second example is that suppose if you go in a suppose if you go for what you can say sandy land, that means a land which contains more sand. Okay, then in that case we are unable to move fast. Okay, that means if we can move on the sand, heavy sand, we are unable to move faster, people. Whereas if you can see camel move as usually without any big difference on the sand. Okay, so why? Because why camel will move as usual comparatively human beings. So that is also related to pressure only. So pressure P is equal to again F by A compared to the human foot. Okay, we have 2 foots, camel has 4 foots. Okay, that is one thing. And area of cross section of the camel foot also more compared to human foot area of cross section. so that our area of cross section is less, so that pressure will be more. Pressure will be more. In that case, we are unable to move faster on the sandy surface. Whereas in the case of camel, area of cross section is more. That means pressure will be less, even though for same weight. Then camel will move faster. Are you clear this, all of you? Second example. Understanding about the pressure? Yes or no? Okay. So once you can understood regarding this, so we need to go for pressure of a fluid. Pressure of a fluid. Can take this. One minute. So we'll go for next page, so that you can start a pressure of a fluid. Pressure of a fluid in a container. Okay. Suppose you can take a container, a vessel. This is a container, like a cylindrical in shape. Inside that you can fill some fluid. Fluid means, let us say, some water. I have taken a liquid. You can take liquid or gas, no problem. Up to certain level. So comparatively gases, liquids also randomly will move, gases will move fasterly. So anyway, you can take any fluid. The molecules of the fluid will move randomly inside the liquid. So these liquid molecules or liquid particles will move randomly and hit, that means collide between them, or they may collide with the walls also. They may collide between them and they may collide with the walls of the container. So due to the collision between the molecule and the wall, there is a momentum exchange. There is a linear momentum exchange between the liquid molecules and walls of the container, and they hit normally like this. So that momentum exchange, that is what delta P, momentum exchange. So delta P per unit time, delta P by delta T. Delta P by delta T, what it will give? Change in momentum, force, na? Rate of change in momentum. Have you remember? Force. So that a force will exert by the liquid on the surface of the container. Suppose this force exerting per unit area on the surface of the container, again you will get the pressure. Are you clear how the pressure will be mounted or exerted by the liquid onto the surface of the container? So the liquid, you can imagine like the liquid molecules or gas molecules trying to collide each other or collide with surfaces of the container. So because of the collisions, it will bounce back again. In that case, there is a momentum exchange. The rate of change of momentum per unit time, you can take the force. Then that force acting per unit area of cross section, normally you can call it as the pressure developed on the surface of the container. That's why the pressure will be developed. Are you clear this point, all of you? Pressure P is equal to F by A. Yes. Suppose whether this pressure developed or not, how to understand? Simply, suppose you can put a small hole here at some place of this cylindrical vessel. Then immediately what happen? If you put some small hole, immediately what happen? That fluid inside will be rest or will come outside? Immediately will come outside with high pressure. Yes or no? Immediately will come outside with high pressure. Okay. So from that you can understand there is a pressure exerting by the fluid onto the container. So here one important point. Will this pressure will be same at all the levels for the liquid container? Will the pressure will be same or different? Vertically and horizontally. Okay. Suppose this container height, let us say h. Let us say h, this container height. So that the point is here at one horizontal level. At one horizontal level, okay, the pressure exerted by the liquid will be same for all the surface of the container. At one horizontal level, you can see the force acting like this. Okay, if you go down or if you go up again, the pressure will be differed. Okay, at one horizontal level, the force acting per unit area will be same, so that at one horizontal level, the pressure will be same. Pressure will be same by the liquid. So for that only this diagram is given. You can see this diagram. So in this, the same pressure is felt by the small light piston exerted by a liquid in any direction of the tube. So one horizontal level, you can see the tubes like this. These are the tubes. Okay. So here inside this, here liquid, you can imagine all the directions liquid is acting. So here there is a piston. Here there is a piston, here there is a piston, here there is a piston. These are all pistons connected with some spring force, spring inside. So that all the levels of the piston is same, you can see here. These are interconnected. So from that, what you can understand, the compressive force given by the liquid at this point, central point, is same in all the directions at one horizontal level. At one horizontal level. This is a like a theoretical understanding at same horizontal level, how the force acting equally. Okay. So by the compression of all the springs are same, so that same force is acting by the liquid or a gas. So from this you can say same horizontal level, the pressure will be same. Are you clear this point? For the container?
Yes, sir.
Right. Then variation of the pressure with respect to height, then we can see. Okay. Then with the height is changing, then what happened? So next topic is that variation of the pressure with the height. You can say height or depth. Let us say depth. Variation of pressure with the depth. So that depth, let us say some h. Okay. Now you can see again the same. You can take a container. First you can take a vertical tub. We can take like this. There is a tub. So in this you can take some liquid will be filled. Imagine like this is like a cylindrical shaped tub. Okay. Cylindrical shaped tub, bottom and top. Now in that the liquid is filled. Let us say some water. Are you clear this? Now let us say capital H will be the height of the container. Okay. So now outside, this is outside, topmost point, this is the bottom. So to understand the variation of the pressure with height or depth, here with the depth you can say, you can imagine one imaginary cylindrical layer, cylindrical liquid layer. This is the imaginary cylindrical liquid layer. Okay, this uppermost point, let us say point P, lowermost point, let us say point Q. Uppermost point, let us say point P, lowermost point, let us say point Q. Okay. Then there is a height small h, difference between uppermost point to smaller, lowermost point. So this imaginary column, imaginary cylindrical column of liquid I have taken. Topmost surface you have take point B, lowermost surface point Q. Then imaginary surface area of cross section, let us say capital A. Let us say capital A, both sides, area of cross section. Suppose due to upper side liquid, there is some force acting on the surface at point B. So that force, let us say F1 force acting from upside liquid towards downside. Similarly, the lower side liquid acting at a point Q, there is a force F2. Let us say force F2 acting from the bottom side liquid on this imaginary cylindrical column F2. Okay. Then pressure at point P due to the force F1, tell me. Pressure at point P. Pressure at point P due to the upside force F1. Then you can write pressure at point P is, let us say P1. P1 is equal to what you can write? F1 by area of cross section A. Then from this, the force you can write as F1 is equal to P1 into A. Let us say equation number 1. Then the force F2 acting at point Q. Then pressure at point Q. Then force, the pressure P2, let us say P2 is equal to F2 by A, force. Then from this you can write F2 is equal to P2A. That means I have taken pressure P1 at topmost point, pressure P2 at the lowermost point, force F1 topmost point, force F2 lowermost point. Area of cross section will be same. Now at equilibrium, suppose this imaginary liquid column is at equilibrium or at rest. Then the force acting upward direction, upside to downside, is equal to the force acting downside to upside. So other than these two forces, any other force acting? Anybody can guess any other force acting on this cylindrical column? There is some weight acting vertically downwards. So there is some mass, let us say m mass of liquid. Imaginary column liquid is m mass. Then mg is the weight acting vertically downwards. mg, yes or no? So mg is acting vertically downward, F1 acting vertically downward, only F2 acting vertically upward. Then at equilibrium, I am writing it the left side. At equilibrium, that means the liquid column at rest means the force acting upside to down, that means F1 plus mg. F1 plus mg will balance the force acting downside to up, F2. Are you clear this step? On the imaginary liquid column, F1 plus mg should be is equal to F2. What is F1 value? P1A. And what about m? Suppose let us say rho be the density. In terms of density, right? M value. Then m mass is equal to rho density into volume of the liquid. Volume of the imaginary container. Imaginary column. And then rho volume means what I can say? Area of cross section into height h, small h. Because small h is inside imaginary column only. Okay, then m we can write density into volume into rho A. Volume you can write area of cross section into height, then rho AH. Okay, then I can write mg means F1 is you can write P1 into A. F1 is P1 into A plus m means rho AH into G is equal to F2 is equal to P2 into A. So for that I have imagined P1 is the pressure at the topmost point P and the P1 is the pressure at the topmost point P, P2 is the pressure at the bottommost point Q. So that P1A plus rho A Hg is equal to P2 into A. Are you clear this equation, all of you? Understood?
Yes, sir.
Then A is common now, all the sides, then you can remove the A. Then P1 plus rho Hg is equal to P2. P1 plus rho Hg is equal to P2. Okay. Then from this, we can define the pressure variation from topmost point to bottommost point. That is, P2 is equal to P1 plus rho Hg. P2 is equal to P1 plus rho Hg. From this, what you can understood? While going to depth of the liquid or a fluid, then pressure is increasing. Okay, P2 is equal to P1 plus rho G. How much increasing? It is H times height or depth times. How much depth? That many times it is increasing. Okay, then pressure difference, if you can see, P2 minus P1 is equal to delta P is equal to rho Hg. Pressure difference from topmost column to bottommost column is equal to rho Hg. Okay, and this pressure difference you can call it as delta P also. And this pressure also only because of what? Gravity acting, G. Suppose if gravity 0, suppose if you can take the same container to the gravity free space, in that case G0 in the gravity free space, then what happen? Delta P will be 0 now. In the gravity free space, delta P will be 0. That means vertically also pressure will be same at all the points. So that vertically pressure is changing because of the gravity only. You have to understand. Are you clear this point? Then you can write for the total height of the container, capital H is the total height of the container. Let us say bottommost point, you can imagine P2 same pressure. Then P2 is equal to bottommost point, and the topmost point you can take let us say P0 atmospheric pressure. So P2 is equal to P1 replaced with P0 plus rho capital Hg. P2 is equal to P0 plus rho capital Hg, where P0 you can take outside pressure on the surface of the container, that is P0 atmospheric pressure. Atmospheric pressure is the P0 I have taken. Then P2 is the pressure at the bottommost point of the container. P2 is equal to P0 plus rho capital Hg. Okay. So atmospheric pressure how to calculate? By using barometer. You can measure the atmospheric pressure. Are you clear this point? This is about the variation of the pressure with the depth H. Yes. We'll go for that equation. Pressure at the depth P, if we can take, then P is equal to, or P at a depth H, PH is equal to the lowermost point, P0 outside pressure plus rho capital Hg. Okay. Pressure at the lowermost point. So instead of PH, let us say P. Okay, P is equal to P0 plus rho Hg. So this is the P is the variation of pressure with depth. P0 is the atmospheric pressure. Then the pressure difference, P minus P0 you can take. P minus P0 is equal to rho Hg. Okay. Suppose you can draw the plot or the graph. Okay. What you can see here along x-axis and y-axis. You can see here. So along x-axis you can take H value. Along y-axis you can take pressure value. So initially at H is equal to starting pressure value from the depth. So H is not height, depth you can take. At a depth is equal to 0, that means topmost point of the container. Let us say depth 0 means initial pressure is P0. H0 means initial pressure value how much? P0. Then you can increase the depth value. Then what happens? Proportionally with respect to H, pressure is increasing. Let us say like that. H value 1, 2, 3 like that. Then you can observe here, this graph shows like a straight line from this point to this point like this. Are you clear this? It's about understanding about variation of pressure with the depth H. Okay, so initial pressure at the topmost point is P naught. After that, pressure is increasing. Okay, so the pressure depends on what factors here we have to understand. Pressure depends on what factors? Vertically. Pressure depends on, you can see here one atmospheric pressure, P naught that is. Okay, this is the pressure of a column of liquid. Pressure of column of liquid depends on what factors? Pressure of column of liquid depends on what factors? One is atmospheric pressure. One is atmospheric pressure. Second is rho, density of the fluid, density of the liquid. Third is the height or depth, h, of the fluid or liquid. Either small h or capital H, no problem. Okay. Next, fourth one, acceleration due to gravity at that place. Acceleration due to gravity at that place. Are you clear these points? Pressure of column of liquid depends on atmospheric pressure, density of the liquid or fluid, and the depth h, and then acceleration to gravity at that point. If the gravity is 0, then immediately pressure will become 0, pressure difference will be 0. Okay, one atmospheric pressure we know already, that is equal to 1.013 into 10 power 5 pascals. Okay, so and pressure is independent of here mass of the fluid or liquid. Are you clear here? It is independent of mass. Okay, depends on the density and the height, independent of the mass. Okay, that we need to understand. Okay, right. Suppose you can take a small example to understand more clearly. Suppose you can take a containers like this. So I'll show the containers like this. Okay, I'll draw the containers. Suppose one container like this, another container like this, another container like this. Same level you can fill the water. I think time less than 1 minute. So this example I'll discuss tomorrow. So this is about variation of the pressure with depth. Okay, and we discussed about the pressure of a fluid or liquid and the variation of the pressure with the depth. What are the factors that it depends? Okay, so I'll stop here. I hope all of you understood. Thank you one and all. Have a nice day.
Thank you, sir.